Mechanical energy, how do we define it? We define it that it is the form of energy that can be converted completely and directly to mechanical work by an ideal mechanical device such as an ideal turbine. All right. And we say that kinetic and potential energies are the essential part of mechanical energy. If a fluid is moving, the essential part of mechanical energy with that flowing fluid would be the kinetic and potential energy of fluid. Clear? But there is another additional term. So these two energies, which is the kinetic energy and the potential energy, they are recognized form of mechanical energies. We already know that. The additional term, which is affiliated with the energy of a moving fluid in terms of per unit mass, is basically this term, pressure divided by the density. So per unit mass, if you're expressing V square over 2 is the kinetic energy, Gz represents the potential energy, and this additional part, which we'll see how is it affiliated with the energy of the flowing fluid, we'll see that it is pressure divided by the density of the fluid. We'll see a derivation for that. All right. This is expressed in per unit mass. If you have to express this energy in terms of rate, that means the rate of mechanical energy of the fluid, you basically has this E with the subscript of mechanical representing the mechanical energy, and a dot on top is basically representing the change in quantity with respect to time. That in thermodynamics, if you see a dot on top of a dimension, it means that you are expressing with regards to time. You are expressing the rate of something. Clear? So it is basically the total energy with regards to time, change in time, or the rate of mechanical energy per unit, rate of mechanical energy of a flowing fluid is basically the mass flow rate of the fluid. Again, mass flow rate is what? Kg per second multiplied by the mechanical energy of the fluid per unit mass. That means the energy which is in kilojoules divided by the mass of the system. So essentially you would have kilojoules per second as the rate of energy. Clear? Is this point clear? All right. When you have an incompressible flow, incompressible fluid means the density is not changing. If the density is not changing, the mechanical energy change of a fluid can be expressed in terms of this per unit mass. Change in mechanical energy can be expressed in terms of change in pressure, change in velocity, and change in elevation, obviously with the corresponding constants. Clear? Is this point clear? Moving on, we say that the rate of mechanical energy of a fluid during incompressible flow. Ji, sorry, you have a question?
सर ये जो अभी आपने एलिवेशन वगैरह का बताया था ये जरा रिपीट कर दें.
नहीं, एलिवेशन का बताया था, क्या रिपीट कर दूं? इसमें क्या चीज रिपीट कर दूं? एलिवेशन इज बेसिकली जी
सर ये जो फ्लो पर यूनिट मास के नीचे जो ये सारी इक्वेशन बनी हुई है सर, इसमें ये जो स्पेसिफिक फैक्टर्स हैं तीन जो आपने हाईलाइट किए हुए हैं, एक P2 वाला, एक V2 वाला और एक क्या कहते हैं जो G into Z2 minus Z1 है, ये हर एक मतलब किस चीज को रिप्रेजेंट कर रहा है, ये पूछ रहा हूं मैं.
The first portion is asking what are these three components representing. This first portion, this one, is basically the energy of the flowing fluid. We'll see what is meant by the energy of the flowing fluid in the next slide. All right. So hold on for that. This change in velocity square is basically representing the kinetic energy, change in kinetic energy of the fluid. And this Z2 minus Z1 is basically representing the change in potential energy of the flowing fluid. Clear?
Yes, sir. Thank you.
Per unit mass, yes, it is per unit mass, but it is essentially expressing kinetic form of energy and potential form of energy. All right. So the rate of mechanical energy change of fluid during incompressible flow can then be represented by, when you have to express the whole energy per unit time, what you'll do is that you will plug in this change in mechanical energy per unit mass into this equation, and you will get basically mass flow rate multiplied by the change in energy per unit mass. Clear enough? Is there any doubt? किसी को doubt है? All right. And this is basically expressed in kilowatts. That means energy per unit time or kilojoules per second. Clear enough? Now we'll try to understand what is the energy of the flowing fluid. We know that energy of the flowing fluid, or energy of the fluid due to its velocity, kinetic energy of the fluid due to its height or change in elevation is due to potential energy. What is the energy of the flowing fluid? So let's assume you have this control volume. I'll highlight this control volume for you. So this is my control volume. All right. And we see in a control volume, there is mass that is being flowing through the control volume. So there is certain mass that is entering into the system, and there is certain mass that is leaving the system. Clear? All right. If I select a certain volume which is outside this control volume, let's say I have this portion or this volume of uh, the flowing material that I have taken out. All right. Now, this volume has to enter into the control volume. This is the case. If the fluid has to flow, this volume has to enter into the control volume. And let's say this volume that I have taken has a volume of V, and the pressure within this region is P. Clear? Now, there has to be certain force that would push this fluid into the control volume. If the fluid has to flow through the control volume, we have to apply certain amount of force onto this control volume, on this selected volume, so that it gets into the control volume. Clear? Is this point clear? And we represent the force by letter F. So there is certain force that has to be applied onto the selected volume so that it moves into the control volume. And this force is to be applied where? On the cross-sectional area of the fluid. Throughout the cross-sectional area, you have to apply this force so that it moves into the system. Clear? All right. So what is this energy, or what is this force that needs to be applied into the system? Or so the force is essentially equivalent to the pressure which is resisting the flow multiplied by the cross-sectional area on which the pressure is acting. This is the cross-sectional area A over here. This highlighted region is basically the cross-sectional area. Clear? So this is the force that you have to apply so that this volume moves into the control volume. So far is it clear? किसी को ऑनलाइन इस यहां तक किसी को डाउट है या किसी को कोई एम्बिग्विटी?
No, sir.
No, sir.
All right. So let's say that the length of this volume that I have chosen, this length is basically represented by the length L. All right. If all of this region that I have selected, it has to move into the system, what is the distance this selected volume would have to travel so that it enters completely into the control volume? Clear? So the energy required to do this is basically, energy is work done. The energy required to do this is basically force multiplied by the force is basically this portion, pressure into area, multiplied by the length. So this is the energy that has to be supplied to this much control volume so that it moves into the control volume. Clear? And where would this energy come from? It would come from the fluid which is behind it. So the fluid behind it would exert this much amount of energy so that the fluid in front of it moves into the control volume. Clear? Similarly, the fluid that is moving out, the fluid behind it would exert same amount of energy so that the fluid moves out of the control volume. Clear? This is the energy of the flowing fluid. If this energy is available, the fluid would move into the system and move out of the system. If this energy is not available, the fluid would not be able to move. Clear enough? Is this point clear? All right. So let's have a look that we have selected this force, or we have identified the force acting on this small light bluish color volume as pressure into area. And if this force is applied through this distance L, the work done in such a way would be PA into L, and A into L is nothing but the volume that you have selected. Clear? Pressure of the fluid itself which is resisting the motion. जो उस कंट्रोल वॉल्यूम, जो छोटा वॉल्यूम आपने लिया है उसके अंदर जो प्रेशर है which is resisting the motion of the fluid. Clear? Now once you have the work done identified, you say it is pressure times volume. If I have to express this work done in per unit mass, what do I have to do? Divide by the mass of the system. So for unit mass, it would be pressure multiplied by the specific volume, which is volume per unit mass, or pressure divided by the density of the fluid. Clear? So this is essentially the energy of the flowing fluid which keeps the fluid moving. Clear? It is this energy which is making the fluid enter into the control volume and then exiting the control volume. Clear enough? All right. Moving on, I have an example for you that you have a site where wind farm is observed, and the wind flowing or wind speed in that farm is basically 8.5 meters per second. You have to determine the wind energy per unit mass for a mass of 10 kg and for a flow rate of 1154 kg per second for air. So the information given to you is that there is a location where wind is flowing at an average speed of 8.5 meters per second. You have to calculate the energy associated with that wind. Now, there is no information given about the pressure change. As the wind is flowing, there is no pressure change. So the fluid flow energy, which is related to the pressure change, is essentially not present or zero. Since there is also no mention of the change in height of the fluid as it is flowing, you will assume that the potential energy change is also zero. So the only energy associated with this speed of wind would be the kinetic energy. And how do you calculate the kinetic energy? For per unit mass basis, V square over 2. So you will express the kinetic energy with small e, that is the total energy of this fluid is basically the small kinetic energy per unit mass, and it is V square divided by. Is this point clear? Then he says that you have to calculate for a mass of 10 kg. If you have a mass of 10 kg, you have to calculate the total energy. How do you calculate it? You know that the energy per unit mass is 36.1 joules per kg. So for a mass of 10 kg, the energy would be what? Definitely multiplied by the mass. So when you multiply it by the mass, you have the total energy. Then he says that you have to express, or you have to find out the energy for the flow rate of 1154 kg per second. Now, when the flow rate is given, something is given with respect to time, mass flow rate is given with respect to time, you'll find out the energy also with respect to time. That means you have to find out the energy which is kilojoules per second. Is it clear? So how do I do that? I basically multiply the mass flow rate with the energy per unit mass. If I multiply the mass flow rate given to me, which is essentially kgs per second, with the energy per unit mass, which is joules per kg, the mass would essentially cancel out, and I would have joules per second, or if I divide by 1000, I would have kilojoules per second, which is kilowatts. Clear enough? All right. Moving on, energy transfer by heat. We have to understand how is heat defined in thermodynamics. It says that the form of energy transferred between the systems or between two systems by virtue of temperature difference. So whenever there is energy flowing due to temperature difference, it is due to heat. Clear? For instance, you have a system which is the can of soda. If it is at 25 degrees centigrade, there is no heat transfer taking place. If it is at 15 degrees centigrade, you have heat transfer taking place because there is a temperature difference between the room air and your system. Similarly, if the can is at 5 degrees centigrade, there would be more heat transfer taking place because again there is a temperature difference between the system and the surroundings. And it says that there are two sorts of interaction that takes place for a closed system, one is the interaction due to heat that is taking place. Again, it is taking place at the boundary, and the other is in form of work. These two energy transfer or energy transfer mechanisms takes place when you are dealing with the closed system. Clear? All right. Traditionally, all right, heat, how is it expressed? Heat transfer. Heat transfer is normally expressed in terms of letter Q. So when you have to express heat transfer per unit mass, you will have the small q representing the heat per unit mass or heat transfer per unit mass, which is the capital Q heat transfer divided by the total mass for which it is taking place. Clear? Or you may have amount of heat transfer given in the form of rate. So when it is given the amount of heat transfer given in the form of rate, you'll have a dot on top of it. That means energy per unit time. And if you have to calculate the total energy transferred, you will multiply it by the duration you are interested in. Clear? In case you don't have any, that heat transfer rate is not constant, how would you calculate the total heat transfer? If heat transfer rate is changing with regards to time, how would you calculate the heat transfer, total heat transfer?
Integrated, sir.
Yes, you will integrate it. So if the heat transfer rate is not constant, you have, it is changing with regards to time. So you have to integrate the heat transfer rate with regards to time from time 1 to time 2, whatever time you're interested in, provided you have a relationship between the heat transfer rate and the time. Clear? This is also simulated over here where you have a room in which heat is transferred. The amount of heat transferred is 30 kilojoules. The mass of the system is 2 kg, and this heat is transferred in 5 seconds. So the heat transfer rate is basically 30 divided by 5, which is the amount of heat divided by the time in which it took place, which gives you 6 kilowatt. This is the heat transfer rate. And the heat transfer per unit mass represented by small q is basically the total heat divided by the total mass. Clear? All right. Now, remember that energy is recognized as heat transfer only as it occurs through the boundary of the system. If I have this potato, hot potato, it has 2 kg of thermal energy stored in it. As this energy is transferred from the system to the surroundings, at this point where it is transferring to the surroundings, it is recognized as heat transfer. Clear? Otherwise, if it is stored in the surroundings or if it is stored within the system, it is not recognized as heat transfer. Heat transfer only takes place at the boundary of the system. Whenever there is heat going out of the system at the boundary, you will refer to it as heat transfer. Or whenever it is traveling into the system at the boundary, you would refer to it as the heat transfer. Clear? Is this point clear? All right. And an adiabatic system is a system in which essentially there is no heat entering into the system or leaving the system. So at the boundary, there is no transfer of heat. Clear? All right. Moving on, the historical understanding of heat was that it was a colorless, odorless, tasteless fluid that was poured from the hotter body to the colder body. Clear? It was recognized as the fluid, and the heat transfer was only understood to be that it is some fluid that gets transferred from hotter body to the colder body. That was the only perception of heat. But later on, this understanding was changed, and the kinetic theory said that it basically is molecules or balls that possess kinetic energy. Heat is defined as the molecules or balls, tiny balls having kinetic energy. Clear? And this was the original theory where the colorless, odorless, tasteless, invisible fluid, which was termed as heat, was defined as caloric. This was later proved on to be wrong. Why? Because they say it is not the heat transfer only which could, or it's not only the movement of the fluid that would generate heat. If you rub your hands like this, mechanical work could also generate heat. There is no movement of the fluid that is taking place, or there is no transfer of fluid from hotter body to the colder body. Mechanical work could also generate heat. So this original definition, which was the caloric, uh, or which was associated with the fluid movement of the fluid, invisible fluid, was proved to be wrong. The heat transfer mechanisms, broadly, you know that there are three mechanisms. One is conduction, in which the energy from more energetic particles is transferred to the adjacent particles which are having lesser energy. So if this atom is vibrating at a very high energy and this atom is not vibrating with high energy, this high vibration would ultimately translate it to this atom and this would move on throughout the solid. This is the way you define conduction. Convection is basically where both the conduction part is there and convection part is there. That means if you have this solid surface and atoms are vibrating in this surface, and if a fluid moves on top of it, this vibration within the solid would translate the energy to the fluid particles just next to the surface, and this energy would then be circulated throughout the fluid. Clear? And radiation basically involves the transfer of energy due to electromagnetic radiations. uh, Energy transfer by work is basically the force acting through a distance. That means a rising piston, a rotating shaft, an electric wire crossing the boundary of the system. They're all work interactions. Formally, the sign that is given generally is that heat transferred to a system or work done by a system are considered to be positive, and heat transfer from the system and work done on the system are considered to be negative. But this is a slightly confusing convention. What we'll do is that we'll stick to heat transferred to the system is Q in. We'll stick to the convention of in and out, into the system and out of the system. Heat flowing into the system is Q in. Work done on the system is basically work in. Work done by the system is work out, and similarly heat moving out of the system is Q out. Clear? I'll show you. Work done per unit mass is what? Capital W divided by the mass. Clear? Power is basically work done per unit time. So if you have 30 kilojoules of work done in 5 seconds, your power is basically 6 kilowatts. All right, 6 kilojoules per second. Clear? Similarly, work per unit mass would be 15 kilojoules per kg. Clear? Now, the conventions that you will be using in your energy balance equations would be this. If heat is moving into the system, you will say it Q in. If heat is moving out of the system, you will represent it as Q out. If work is done on the system, you will say work in. If work is done by the system, you will say work out. Clear? This is the convention we'll stick to in our equations. We'll not stick to whether it is positive or negative. We'll stick to these conventions. All right? Heat versus work or heat work, both are recognized at the boundaries. This is a very important point, that both these interactions are recognized as the boundaries. Heat and work are boundary phenomena that take place at the boundary of the system. System possesses energy, but they do not possess heat or work. If I define the state of the system as state 1, it means that it has certain amount of energy at state 1, but it is not heat and work that could be defined at those states. All right? They take place or they result in the form of a process. Heat and work are basically related to the process. They are not related to the state of the system. So they have no meaning at state. Like you have a meaning of pressure or volume at a state. At a fixed state of a system, you have fixed pressure, fixed volume. But there is no fixed work at a state. All right? We'll see how. They are path functions. How? If I'm moving from state 1 to state 2, that means I am moving from 2 meters cube to 5 meters cube. The change in volume is what? In both the cases, it is 3 meter cube if I move through process B or process A. In both the cases, it's 3 meter cube. That means volume is a state function. It is dependent upon the state. If I fix the state 1 and 2, the change in volume would always be the same. Clear? But this is not the condition with heat and work. Even if you have fixed the states, the way you perform the process would define the energy associated with it. That means for process A, the energy is 8 kilojoules, and for process B, the energy is 12 kilojoules. It would change with regards to the process. And that is the reason normally when you express the state functions, the change in state functions, volume is a state function. If you want to express the change in volume, you express it with dV, change in volume. All right. But when you're talking about the process, change due to a process, that means work done as I moved through process A. It is expressed in terms of inexact differentials. That is this way. Clear? Is this point clear? Anybody who has doubt in this?